Welcome. I'm Dr. Larry Sterna. This is the first video in this course on electricity, magnetism, and optics. We begin with a study of electricity and the most fundamental concept in electricity, that is, charge. Hope you enjoy. Let's begin. Here's a portrait of a man named William Gilbert. It's taken from the book called Practical Physics, written by Millikan and Gale. Now, who is William Gilbert? And why did Millikan and Gale refer to him as the father of the modern science of electricity and magnetism? Well, Gilbert was an English physicist and physician to Elizabeth I and James I. And it was Gilbert who explained that the reason a compass needle points north is because the Earth is a magnet. Earth has its own magnetic field, similar to that of a bar magnet. It was Gilbert who introduced the word electricity into the English language. He took it from the Greek word electron, you see written there, which is the word for amber. The Greek word for amber, which is fossilized tree sap. Now, why is electricity associated with amber? Well, it turns out that amber is an excellent insulator. And if you take this material and rub it against other materials like the fur of a cat or the wool of a sheep, this amber obtains the property that is called charge. Or we say that the amber becomes charged by rubbing it. Now, since electron is the Greek word for amber, and this amber will become charged, Gilbert associated this charge with electron. He introduced the word electricity into the English language. What he found was that many different materials can be electrified. That is, they can become charged when you rub them together. It doesn't work if you rub a material against itself. You must rub two different materials together. When you do this, one of them becomes positively charged, the other becomes negatively charged. This is called triboelectricity. Tribo is from the Greek word, which is to rub or friction. It's the electricity that comes from rubbing things together. But why was this so significant? It was significant because Gilbert demonstrated it was very easy to generate charged objects. And once you can easily generate charged objects, you can study electricity in the lab. Let's consider the definition of what is electricity. Here's a statement I like to use. Electricity is an excess of positive or negative charge, which is localized. We call that static electricity. Or in motion, we call that electric current. Now, we said that the concept of electricity and charge was developed by rubbing different materials together. What people found, there are two types of charge. They called one positive and one negative. And whenever you have an excess of one or the other, either localized or in motion, you have electricity. In other words, it's all about charge. Electricity is not confined simply to electrons. Electrons, we'll see later, are, of course, very significant in electricity. But whenever you have positive or negative charge, one of them in excess, you have electricity. You can talk about electrical phenomenon. Now, the symbol we use to represent charge is Q. Typically, might use a lowercase q to represent a smaller charge, uppercase Q to represent a larger amount of charge. In either case, we'll use the symbol Q to signify charge. Now for a little terminology. Conductors and insulators. Conductors are those materials in which charges can move freely. Now, when I say charges, I don't mean all the charges in the conductor. At least some charges can move freely. For instance, in a metal, it's only the electrons that can move freely. Now, other materials are called insulators. So think of an insulator as a material where charges cannot move, but when we say they cannot move, we mean over large distances. For instance, we know electrons move within atoms and molecules, but they don't move from one end of a piece of material to another if that material is an insulator. Now, both conductors and insulators can have static charges. Because something is a conductor doesn't mean that the charges have to be moving. You can store a static charge on a conductor. You'll see that when we study the capacitor. The fact that something is an insulator does not mean it cannot have a charge. It can have a charge, but it will be static. Only conductors can have electric currents. Electric current is when the charge or some particular charge can move one end of a material to the other, such as an electron going from one end of a wire to the other. Now let's consider the properties of charge. I said when two different materials are rubbed together, the two different materials obtain different types of charge. One type is called positive, one type is called negative. Now, what was discovered is that charge is always conserved. If you started with two neutral objects, you rub them together, different materials. On one, you would have a certain amount of positive charge. On the other, you would have an equal amount of negative charge. In other words, charge is always conserved. You start with something neutral, you can separate it into a positive and negative part. If you started with an object with a positive charge, there is no way to destroy or remove that positive charge other than adding it to an equal amount of negative charge. You can separate or combine charges. You cannot create or destroy them. Another property is that there is a quantum of charge, meaning there is the smallest possible amount. Charge occurs in multiples of Q sub E, the elementary charge, the smallest possible charge. Now, we're going to take Q sub E to be a positive number. Therefore, consider an electron, smallest negative charge would be negative Q sub E. Here's a list of the atomic particles. These are the three things, the electron, the proton, the neutron, make up all atoms. Let's consider the mass and the charge of each one of these particles. The electron has the smallest mass by far, 9.11 times 10 to the minus 31 kilograms. This small mass, very, very significant. Its charge, minus 1.60 times 10 to the minus 19 coulomb. You see in the parentheses next to charge is a capital C that stands for coulomb. That is the unit of charge. The proton has a significantly larger mass than the electron. The mass of the proton, that 1.67 times 10 to the minus 27 kilograms, is more than 1,800 times larger than the mass of the electron. Very significant. Its charge is a positive 1.60 times 10 to the minus 19 Coulomb. What's especially interesting, the proton, the electron have opposite charge, but they have the same magnitude of charge. But the mass is very, very different. Proton, more than 1,800 times more massive than the electron. Neutron has a mass essentially to the same as the proton to 3 significant figures, but 0 charge. The neutron contributes to the mass of the atom, but not to the electrical properties of the atom. Now, the elementary charge, which I introduced earlier, Q sub E, is equal to 1.60 times 10 to the minus 19 Coulomb. So the electron, we could express its charge as minus QE and the proton as plus Q sub E. The important point to make, and we'll see this in later videos, electrical forces are proportional to the charge. Let's consider Newton's second law. F equals ma. Force is equal to mass times acceleration. Since electrical forces are proportional to the charge, in general, electrons and protons will experience similar electrical forces. However, they're going to respond very differently. If I rearrange this equation, the acceleration is equal to the force divided by the mass. Therefore, if an electron and proton experience similar electrical forces, the accelerations will be very, very different. The electron is going to accelerate more than 1,800 times greater than the proton because its mass is so much smaller. This has enormous significance. It means that in general, the electrons will respond to electrical force much, much more rapidly than the proton. Now, atomic nuclei consist of protons and neutrons. So that large massive nucleus is not going to respond to anything like the extent to which the electrons will respond to an electrical force. That is why you study chemistry. You talk about how you form ions, gaining an electron, losing an electron, how you form bonds. You have 2 electrons pairing up to form a bond. It's the electrons that are so significant in chemistry because of their ability to respond so rapidly to electrical forces. Now, you saw in the previous slide, we had some very tiny numbers to work with. Those masses, those charges, etc. So those powers of 10 can be rather tedious to work with after a while. Therefore, it's good to have a system of abbreviations for powers of 10. This table here, extremely important because the use of these units is not restricted to physics. You have it in chemistry, you have it in biology, you have it in medicine, you have it in computer science with data storage and processor speed. So I recommend you memorize these, but if it's difficult to memorize them, you definitely should make a table. You can pause this video, make a table of these powers of 10, because we would use a lot of them from those very small numbers, pico, 10 to the minus 12, and we'll probably move up into mega and maybe giga. Let's consider the most common charged species. First on the list, let's consider electrons. They have negative charge. They are going to be critical as the prime actors in electrical circuits. Electrons moving through conductors, moving through wires. What about atomic nuclei, which are positively charged? Well, these really are not going to enter into our study of electrical phenomena. They're not going to really be involved. The next item on the list, ions. These have a great deal of significance. Ions can be positive or negative. Ions are critical in the function of batteries. They're critical in the function of the electrical system and the human body, that is, the nervous system. So in studying electricity, we really want to have an understanding of electrons, negative particles, and ions, which may be positive or negative. Now let's consider the question, or really two questions. What is an ion? What is the charge of an ion? This first example, we start with a sodium atom. The symbol is Na. You don't need to memorize the symbol Na, but you need to know how to interpret the charge of this thing once it becomes an ion. That's what we're going to look at here. We start with a sodium atom, which is neutral, meaning it has equal amount of positive charge in the nucleus, negative charge, which are the electrons around the nucleus. The sodium atom can lose an electron, and this process is illustrated by the arrow pointing to the right. We now form a sodium ion represented as Na with a plus sign, and an electron represented as E with a minus sign. We started with no charge, sodium atom neutral. Now we have released an electron, which has a charge minus 1.60 times 10 to the minus 19 coulomb. Therefore, to conserve charge, the charge of the sodium ion must be a positive 1.6 times 10 to the minus 19 coulomb. Now, in chemistry, you'll routinely refer to the sodium as having a charge of +1. Well, when you say +1, that's simply a shorthand. The actual value of the charge, the number you would use for doing calculations, is the plus 1.6 times 10 to the minus 19 coulomb. You have to understand you need to know the charge in coulombs to work with this in physics. Now, here's a second example. Calcium atom. Again, it's a neutral species, nucleus surrounded by electrons, equal positive and negative charge. Calcium atom can lose 2 electrons. The charge carried by the 2 electrons is 2 times minus 1.6 times 10 to the minus 19 coulomb. Therefore, to conserve charge, the calcium ion, which is written with a charge 2+, which is a shorthand, actually has a numerical value of charge of plus 3.2 times 10 to the minus 19 coulomb. Notice that the ions in both cases, these positive ions, appear much smaller than the atoms. Why is that? Well, because the electrons, although extremely small particles, within the atom, they occupy a large volume and really the electrons determine the size of the atom, they determine the size of the ion. You remove an electron, the ions, the positive ions, are much smaller than the neutral atoms. Now let's consider the case of a negative ion. We start with the chlorine atom, which is neutral, represented there with Cl. We add to it one electron, which carries a negative charge. The result is we form what is called a chloride ion. We have to conserve charge. We started with the charge of the electron minus 1.6 times 10 to the minus 19 coulomb. Therefore, we have to, in the end, have the same amount of charge. Therefore, the chloride ion, which you might say is minus 1, for a shorthand, it actually has a charge minus 1.6 times 10 to the minus 19 coulomb. Notice we added an electron. The chloride ion is somewhat larger than the neutral chlorine atom. If we had added 2 electrons, well, the superscript would be 2 minus, and you double the charge, would be minus 3.2 times 10 to the minus 19 coulomb. To summarize, rule for ions, you add 1.6 times 10 to the minus 19 coulomb for each electron that the atom has lost. Or actually, you can have ions made of combinations of atoms. It doesn't have to be a single atom. And you subtract, or you add minus 1.6 to the minus 19 coulomb for each electron gained. Again, it could be an atom, it could be a combination of atoms together that make up the ion. One point to be noted here, when these processes take place to form ions, you're not adding or removing protons, you're not adding or removing neutrons. It is the electrons that are being added or removed. At this point, I'd like to look at the question, how is electricity produced? There are 4 primary ways to either separate charges or to selectively put one of the charges into motion. The first method we've already discussed, rub different materials together. If you rub 2 different materials together, one of them is typically more likely to gain electrons and become negatively charged. The other is more likely to lose electrons, become positively charged. The second method we've already discussed, chemical reactions. One atom may be more likely to lose electrons. Another atom may be more likely to gain electrons. You can pair these up, and that's the nature of the chemistry within a battery. The third method is called electromagnetic induction. This will be a topic we discuss in some detail later in the course. Simply stated, it is the use of magnetic fields to create electric current. And it works so well. It's why we have electricity that is abundant. The fourth method is called photovoltaic reactions. What is this? This is also called, or more typically called, solar energy. It's the use of sunlight to knock electrons out of a material. Remember, you want to separate charge. So by having the sunlight knock electrons out of the material, you can have the electrons flow through a circuit in order to get back to where they started. And that's the nature of solar energy. This will not be a topic in this course. I'm only including it here because it is one of the 4 primary ways to generate electricity. Now, to better understand how atoms may gain or lose electrons, let's consider a model of the atom. Early model of the atom was the Bohr model. In this model, you have a nucleus represented in that picture with blue and red spheres. The nucleus is sitting in the center, and the electrons are orbiting about, as shown in the picture, those black spheres. Now, although we no longer consider the Bohr model to be correct, this picture is still extremely common. You'll see it in a lot of places. Now, the way we view the model of the atom now is as such. There's a tiny, tiny nucleus located in the center. That picture of the black dot on the right. And an electron cloud, much, much larger, surrounding the nucleus. Now, what is the electron cloud? It's not a vapor of electrons. What the electron cloud represents, it's where the electrons are moving about. As the electrons move, they really define the size of the atom by the volume over which the electrons move. The cloud, these pictures typically represent where there is a 90% probability of finding the electron within that shape. Now, if the electrons are moving rapidly about, and 90% of the time they're within this cloud, then part of the time, electrons may be at the edge of the cloud, part of the time they may be outside of that cloud. Electrons get very far from the nucleus. That's when they have the smallest attraction to the nucleus. That's when they're most likely to participate in some kind of process of gaining or losing an electron. Now, here's the scale of the atom. The nucleus has about 99.98% of the mass, but the diameter of the cloud is about 30,000 times greater than the size of the nucleus. So the electrons, much lighter, travel very far from the nucleus. When they get very far, the smallest electrical attraction to the nucleus. That's why if you have two different materials, rub them together, if one of them has a slightly greater attraction to the electron, the other is slightly less attraction to the electron, those electrons that are furthest from the nucleus might be exchanged from one to the other. So that after rubbing, you wind up with one material being positive, having lost an electron, the other being negative, having gained an electron. Now, although this is a physical process of just rubbing two things together, we can also think of what goes on in chemistry. In chemistry, when bonds or ions are formed, is those outermost electrons that participate. Nucleus doesn't participate in chemistry. The electrons closest to the nucleus don't participate in chemistry. It's the electrons that are in the outermost shells, those clouds, those parts of the clouds furthest from the nucleus. Here's something called the triboelectric series. Now, this is a very partial list. You could take every known material and put it on this list. And what it represents are those things that are more likely to lose electrons when rubbed, and those things more likely to gain electrons when rubbed. Of course, if you rub the same material against itself, you don't get any net change. But for instance, if you take something higher on the list and rub it against something lower on the list, you expect one to lose electrons one to gain electrons. Let's look at an example. Suppose you have cat fur, which is higher up the list, more likely to lose electrons, and you rub it with polystyrene, which is lower down the list, more likely to gain electrons. What you would expect after rubbing these two things together is that the cat fur would become positive, the polystyrene would become negative. Now, we haven't discussed electrical forces yet, but I will tell you, positive and negative charges are attracted to one another. Let's look at an example. Here's a photo taken from OpenStax University Physics Volume 2. Now here's a cat that has either walked through or been rolling around in polystyrene packing chips. Result is the cat fur would have become positive, the polystyrene that was rubbed become negative. Now these chips are stuck all over the cat. So this is a very general phenomenon. You take two materials on that list, you rub them, you expect one to be positive, one to be negative. Now let's look at another situation to illustrate the importance of the electron cloud. Imagine that we have an atom near an ion. So in this picture on the left, we have a neutral atom. There is the nucleus surrounded by the electron cloud. Right-hand side, imagine we have a positive ion. Will it be attracted? Well, the electrons, which are negative, will be attracted to that positive charge. The nucleus, which is positive, will be repelled from it. Therefore, you would think, well, if the atom is neutral, those two things would cancel. There shouldn't be any attraction. However, suppose the ion comes closer to the atom. What will happen? Remember that the electrons are very light. They respond rapidly to electrical forces. The electron cloud will be distorted by this positive charge, which is coming close. Therefore, the electrons will tend to move toward that portion of the cloud closer to the positive ion. They'll have a greater probability of being in the vicinity of the ion. This is called an induced dipole. So the atom has more negative to the right-hand side or positive to the left-hand side. Now, the induced dipole will be attracted to the ion. Why? The dipole is still neutral. However, those electrons are closer to the positive ion. Therefore, they will have a greater attractive force, whereas the nucleus is further from the ion, will have a smaller repulsive force. Therefore, the induced dipole, the neutral atom, will be attracted to the ion. So these kind of interactions can be very important when you study chemistry. That brings us to the end of this introductory video on electricity, where we discuss charge and the importance of the electron. Next video, we'll begin our discussion of the electric force. See you there.